factoring integers, first of all, let me just remind you that integers means whole numbers, both positive and negative. So today we're just working with factoring with numbers, and that's the style of factoring that you guys have already done. So first of all, let's review what factoring is all about. If I said, for example, give me factors of 12. Anybody want to start? Factors of 12. Leanna, give me one set.
4 and no.
Yeah.
4 and 3.
4 and 3. Daniel.
6 and 2.
6 and 2. Izzy.
12 and 10.
Good. Now, I listed them as in pairs. You can do it that way. You can just put them all together. You can put them in number order, smallest to biggest. But remember that factoring means we're looking for sets, pairs, in this case of numbers, because we're just dealing with numbers today, pairs of numbers that would multiply to make the number we started with. Okay, so first of all today you're going to see that it's going to talk about positive and negative factors in some cases. We're not going to worry about the negative factors. Let's try a bigger number. Let's say I say, give me all the factors of 56. Now, I don't expect you to know all of them like you did for 12. I expect you to know all those for 12. 12 is a simple one. A bigger number like this, I don't expect you to know it, but I do expect you to be able to figure it out. First of all, let's start. There's always a factor of 1 and itself, right, for every single number. Now, what I want you to think about is the divisibility rules. We haven't worked on them this year, but we have in the past. For example, is this divisible by 2? And if so, how do you know? Leanna, how do you know?
6 is even.
Good. If the last digit is an even number, then it's divisible by 2. I don't expect you to automatically know what the other factor is that goes with 2, but I expect you to be able to find it. 2 times what makes 56? Now, that might be a hard way to think about it, but if we think that division is the opposite of multiplication, we could go 56 divided by 2, and we get our other factor of 28. So that's what I mean when I say I expect you to be able to find the factors. You may not automatically think 28, but if you know that 2 is a factor, then you need to find the 28. Okay, let's review the divisibility rule for 3. Anybody remember? Vincent?
You add up the numbers and then it's divisible by 3.
Good, we add up the digits. 5 plus 6 is 11. Is 11 divisible by 3? No, so 56 is not. 4, the rule was a little different. I'll tell you 4 is. The rule for 4 was to look at the last 2 digits and see if they divide by 4. Well, that's what we're trying to figure out. This one only has 2 digits. So does 56 divide by 4? Use your calculator. Divide by 4, oh, 14. I got a whole number. I only want whole numbers. So if that had been a decimal, I wouldn't have used it, but 4 and 14. So some of them, just try it. Use your calculator. Will this divide by 5? CJ?
No,
How do you know?
because it's not divisible by
How do you know?
5. Because
What's the rule? Do you remember? It has to end with a
5 and 0.
5 or a 0. Then it would be divisible by 5. Since this doesn't end in a 5 or a 0, it's not. Okay, does anybody remember the rule for 6? Oh, good. Leanna?
If it's divisible by 2 and 3.
Good. If both 2 and 3 worked, then 6 would work. 3 didn't work, so 6 won't work. What about 7? There's no rule for it. So just divide it by 7. Does this divide by 7? Sure. 7 times 8 is 56. Now, this is all of them. However, just be careful that in a bigger number, you might even have bigger factors. For example, if it was 121, 11 times 11. So don't just stop here. We could go to 9. 9 is the same as 3. If we add the digits and the sum divides by 9. So 5 plus 6 is 11. 11 doesn't divide by 9, so 56 won't divide by 9. How do you know if it divides by 10? Well, it ends in a 0. So we have those rules, but then beyond the rules, you also need to be able to think, would there be any others that are any bigger? And in this case, there's not. Okay, so that's the first step, is remembering how to factor. So in some cases, you'll just be finding the factors. Now, prime factorization. This is where we do what we call factor trees. We've done this. This is where you factor down to just prime numbers. And we will write the answer with exponents. I'll show you that. So we are going to do the prime factorization of 504. Now again, we're looking to get down to just prime numbers. So can somebody please remind me what is a prime number? Luke.
A number that can't be divided by anything but 1 in itself.
Good. A prime number, as a reminder in case you are trying to forget, has only 2 factors. And they're always the same, as Luke said, 1 and itself, whatever the number is. So a prime number, for example, 17, only has the factors of 1 times 17. Okay? 2, by the way, is the smallest prime number and the only even prime number. Okay, so let's start with 504. We're going to factor it down until we just have prime numbers. I like to circle each prime number so that I don't forget it in my final answer. I don't expect you to know factors of 504. I expect you to be able to use the divisibility rules. So for example, easy, oh, it ends in a 4. That means I know it will divide by 2. What's the other factor? Well, 504 divided by 2, and I get 252. Now, 2 is prime. Again, the smallest prime number is 2. So I'm going to circle it, and it means that that branch of my little tree is done. Any branch that is not a prime number, you need to keep factoring. How do I know this one's not prime? Well, it ends in an even number, which means it is divisible by 2. 252 divided by 2, 126. I have another prime number. I circle it so I don't forget it at the end. Now, you don't have to keep using 2. There are other numbers that would factor. It should not matter what numbers you use, as long as they are actual factors. For example, for this one, we could have done, let me just get my, we could have done 4 and 63. And if you do it properly, you will still get to the same answer. When there's more than one pair of factors to choose from, it doesn't matter which one you pick. 126. Let's say again we just stick with 2 for this. Oh, well, I know it's going to divide by 2 because it ends in a 6. So I do my 126. Oops, I just typed that wrong. Yikes. 126 divided by 2, and I get 63. What about 63? Factors of 63? I'll tell you right now, it's not prime. Daniel?
7 and 9.
Okay, good. 7 is prime. 9 is not. What factors of 9 could I use? Oh, look at all those guys, so smart. Jaden.
3.
3 times 3. 3 is a prime number. And now I have no more branches that need to be finished. Now all I need to do is take my little circles. And again, I would suggest you circle them or highlight them so that you don't forget them in the final answer. The prime factorization, I'm going to write it with exponents. I'm going to start with my smallest factor, 2. To the power of 1, 2, 3 of them, 2 to the power of 3. And then I'll go to my next number, the 3. There's 2 of them, so 3 squared, and there's 1, 7. This is the prime factorization of 504. You take all of the prime number factors, you write them with exponents, again, 3 2s means 2 to the power of 3. And this is your answer. If you were to multiply this out, you should get back to the original number. For example, 2 cubed, 2 times 2 times 2 is 8. 3 squared, 3 times 3 is 9, so I have 8 times 9 times 7, and I get 504, back to my original number. That's how I know I did it right. Any questions on this? Okay, final thing you're going to be doing. I'm just going to show you an example. We're not going to do another prime factorization since we're short on time today, but let me show you an example of what it would look like. You're going to use this to find the greatest common factor, the GCF, using prime factorization. To find the greatest common factor, you could list all the factors of the numbers and then find the biggest one that's in both lists. But you're not gonna wanna do that if they're big numbers. For example, if I said, find the greatest common factor of 882 and 945. Anybody wanna spend their time listing every single factor of all those numbers? I hope not, because it's gonna be a lot of them. I would not recommend you try to list all the factors of each of these numbers, because I guarantee you'll probably miss one and then you get the wrong answer. So instead of that, we would use the prime factorization. Now what I don't want to do right now is spend the time to do the whole factor tree. But I'll just tell you, for this one, personally, I'd go, oh, it ends in a 5, I'm going to divide by 5. This one, bless you, I might go, oh, it ends in a 2, I'm going to divide by 2. Start with wherever you want to start. You would do the factor tree. I'm just going to give you the answer here. When it's done, 882, we'll have a prime factorization of 2 times 3 squared times 7 squared. And remember, you can always check by multiplying that out. 945 would have a prime factorization of 3 cubed times 5 times 7. Now, here's what you need to do to use that information to find the greatest common factor. From these two answers of the prime factorization, you are going to form the product, so we're going to be multiplying, the product of the smaller power of each common prime factor. And I'll explain what this means. Form the product of the smaller power of each common prime factor. Now the good news is you get to use your notebook for a test. The tricky part of this is that it's greatest common factor, but we're taking the smaller power. But it has to be in common. That means it has to be in both lists. So here's what we do. We look at our two answers of the prime factorization, and we find which ones, first of all, do they have in common. Which factors do both of these answers have? Daniel.
3 squared and 3 cubed.
Okay, so first of all, they both have a 3. And again, if we had the trees, we'd see the little circles and we go, oh, there's 3's in both. Now, you take the smaller power. So between 3 squared and 3 cubed, which one are we going to take? Which one is smaller? Brian? 3 squared. Okay, what else do these two lists share in common? What factors do they have in common? Daniel?
7.
They both have 7s, right? So we look and we go, oh, they both got a 7. I take the smaller power. Between 7 squared and 7, which one is smaller? Roland? 7. Now, just so you know, let me just say, if they were both 7, then you take 7. It doesn't matter, they're the same. You just take one. All right, you go, oh, they're the same size. Well, it doesn't matter which one I take. Take the 7. 5, is that in common? No, this one has a 5 and that one doesn't. 2, is that in common? Nope, this one has a 2 and that one doesn't, so we don't use them. Now, I get my answer. 3 squared is 9. 9 times 7. The greatest common factor of these two numbers is 63. I'll tell you right now, if you were to try to list all these factors, I guarantee I probably would not have found that 882, let me see here, 882 divided by 63, I probably would not have found that 14 times 63 makes 882. I wouldn't have found that if I was just listing them. So for big numbers, if you have to find the GCF, this is the way you want to do it. Now, for the homework, in any of the problems, you might see some examples where they go, oh, but what about negatives? Factors of 12. Oh, well, there's 3 and 4. Or negative 3 times negative 4. We're not going to worry about the negatives for today. Just positive numbers. Okay, so if you see examples in the book where it's got negatives, we're not going to bother with that. Okay, so that's it for today.